How's it going, everyone? Welcome. Javier Gonzalez here, and today let's take a look now at the scope change, which is part of the important thing that we need to know when you're working with any programming language. So right now we are focused our attention to JavaScript, which is this particular language where I have my first exposure, and also I can offer that in a professional way. So, in order to now be competent with the language by understanding how it works and not how it's supposed to, which is a lot of, unfortunately, JavaScript developer. I was one of them that we were paying to be professional guessers, and this is not. I don't think this is not the way. This is not the way. So, in any case, that might be my opinion, but it's not the way because it's not effective. It's spending too much time on doing things that if you know how that works, you wouldn't be in that. You wouldn't be in that place in the first time. You wouldn't be in that place, yeah, in the first. Uh, so, because of that, so I dedicate now all over this series of videos to understand now, based on the book written by Kyle Simpson, a software engineer with over 20 years of experience, where now this is the second version, where he described is not only is the inner mechanisms of the language, these low-level features, iterations, um, uh, yeah, iterations, closure, this, the object, and the prototype change, but also things that are now around these core features, around the JavaScript. So, for example, a programs. What is the type of values that we can have? The uh, the way of how can we define value, what a value mean in the language, how can we define these values as a literal or held inside of a variable, what is a variable, what allows us a variables to do, and what are the different syntax forms that we can have, or that we can define our variables, and also the role of functions in the language as a value, whether it's a mathematical strict definition or a procedures, and how now these values can be compared. What is the mechanism, or how now comparison means to JavaScript, which is based on its equality referential equality, right? And also is now how you can convert from one value to another. So once we lay out these foundations, and then how can we now organize our code in a way that it makes much more easy for us to understand, and to maintain. In the case of JavaScript, we have now different code organizations, a class, functions, and uh, and models. It also is the things that are around now JavaScript, right? So, for example, is the author who makes this, the legal trademark, now the commit that oversees this particularly this spec, on how now this JavaScript implementation must follow must follow, and also is things that are now depending of the spec, and what are the challenges. For example, the TC39 goes, and what are the series of steps in order to a champion or a proposal go all the way up to the top, and now make and be that as a standard. uh, and what is the motto of the TC39, which is don't break the web, and how now they do that by providing now polyfills that allows to now implement these new features, that may or not be in that particular stage or accepted by the or now be part of the spec, uh, but yet implementations uh, or JavaScript implementators, most of the time, JavaScript engines, they don't have that implemented, and they're going to do that at their own pace. So it also is well to understand that the concern around the JavaScript itself, because this is a scripted language, aka it must be interpreted. But the reality is that, in essence, if not in practice, JavaScript is a compiled language. And the concern is that if this language is fast enough, so for example, by putting out some tests, and it has now a great precedent uh, that, for example, ASM, which is a subset of JavaScript that say a bunch where now a bunch of Mozilla engineering wants to test that the language in itself was fast enough by providing hints to the engines so it can now run and so it can do optimizations and running the code much more efficiently. So they pour now is an Unreal engine from C to the web, all right? And also, years later, this WebAssembly, as we know, is now the spiritual successor that is say, hey, instead of actually now having to worry about parsing the source of text into machine readable code, so let's going to skip the parsing phase by using and represent this language in an assembly like, and now execute the code here. So they now create this WebAssembly that is become this universal compiler targets. So no matter which particularly program you have written in any language, is going to now compile to this interpretation into this code that look like assembly, aka web assembly, that you can now run in any environment that runs WebAssembly code. So this is just to describe is the things that are around now JavaScript, as well as the strict mode, okay, which is now a set of guidelines to do the best, or is a set of good practice, or it is a set of rules that enforce JavaScript developers to follow to have a good chance for the JavaScript engines of optimizing and running your code. So all of this is just the fundamentals or this huge overview around JavaScript, from these low-level features and now all the layers that are around that. So because here in this video we want to now dive deep into one of those aspects, which is scope and closure, especially these low-level features. We look first at the to the this particular book of scope and closures. And in order to understand now scope and also variables, which is the most important piece that we have in our code, in any programming language, all right? Because these variables and functions that are defined at author times, it is a scope, it is determined is at compilation or before the code is executed. So this is scope structure, which are unaltered by runtime conditions. It now makes sense to understand this, because if we think, or as we know, functions in JavaScript are values, and we can now hold variables inside of our functions. So this scope structure it will now set before execution. So no matter where we execute this function, all right, we always have this scope structure. This is known as lexical scope. And the reason to understand this scope structure um, is to, well, by looking at the way how now a compiler and the interpreter works, which is the way of how the source text is transformed into machine readable code. This two process is just aiming to do this. It works towards the same goal, which is convert that code from source text into machine readable code. Now, the way it does that is quite different. So in a compiler and interpret it, in a compile, what happens is that it has several steps. So in the classical compiler theory, we have now the tokenizer and the lexing, which is going to convert your source text into tokens that are meaningful to the language, pretty much like when you read an English or a Spanish text. If you're familiar with the language, then you know what's going on, all right? Unlike if you're reading, for example, Chinese or Persian, I don't think it's Persian, is or Mongolian, okay, Farsi. Well, you need to understand that language as a way to understand these meaningful tokens. And this is called lexing because this is more like an academic, is if that particular token is part of another token or is a different token. So this lexing or this parsing phase, which is what happened initially, and then is now that it has all of these strings of tokens, okay, is going to convert that into an abstract syntax tree known as the parsing phase, which is this representation of the code that when it needs to generate the machine readable code, which is the state 3, it actually matters of which language you're trying to compile, as well as the platform you are addressing. So this is now to understand is what compiler is. So in the case of JavaScript, because the language in itself, the observable behaviors, when it comes to now look at how errors are handled. So for example, syntax errors, early errors, and hosting, all right? All of this stuff happens before the code is executed. And I can show you that, but that won't be part of today's video. But the idea here is that because of this behavior, so now we can say that JavaScript, in essence, if not in practice, it acts as a compiled language, not by way of how it is distributed its code, but also by way of how it analyzes it. Okay, so and because the JavaScript engine is a little bit more complex because it doesn't have any build step like this compiler language, and it needs to execute this code in microseconds. All right, so those JavaScript implementations or people that work around that, they have to find some ways to solve this, aka hacks, and just-in-time compilation, and so on and so forth. So, but the thing here is that once we know this, and the other aspect important to understand the scope is that the assignment of this reference and how that happens and when that happens. So for example, if this assignment, when you assign value to a variable, it is part of a target or it is part of a source. So the idea here is that we look that Scope is determined before the code is executed. You can also modify the runtime scope. Unfortunately, you shouldn't do that using the eval. I wouldn't suggest that. Please don't do that. And the other is that lexical scope that happens before. So we look at the scoping with hosting happens is before the code is executed, and it is for us quite relevant to understand that when we use a functions or a variables and blocks and how they relate each other matters because it is determined at compile time. So when we look to illustrate now how the lexical scope works, we use some couple metaphor, or at least Kyle Simpson used a couple metaphors, right? Whether it is the bubbles and how do you put it? Marbles or marbles, buckets, and bubbles. Okay, in order to illustrate now how a variable or a marble fit into a bucket, into scope, and now how that particular scope have a range or the scope. So and another is that the association within this identifiers or this marble and it is value. If we can think of this like a conversation that happens between the scope manager and the compiler initially in order to define is the scope structure, and then the association of those identifiers with its value. So I do think that this is quite really mind-bending and revealing because understanding this particular example, and also we're going to practice. We're gonna. There is no need to practice because once you understand that, you just only go to that. So So right now we are looking here at the scope change. Okay, and you may wonder what is this? Well, because now the scope, which is determined at compile time, and this is when you can define now several of this nested scope inside of that in order to understand it is relationship, right? Whether it's a function or the block and it is variable, right? We do need to understand how this scope change actually works. And this is going into the details by saying that each one of those scope, each particular syntax or specific syntax, usually function and block, now they have an associated execution environment record, which you can think of this like an object, all right, that has now a reference to the outer enclosing scope, and this is known as the scope change. So when you define so you have is the global scope, and then when you define specific syntax like functions or block, is now the engine associating is this. So this lookup is mostly conceptual, and there is now something that is known as shadowing, which is how you can now prevent or shadowing is like how you can now shadowing is like the way of how you can now interfering the variables in the scope change to modify this value. So a good example is with this, right? So this is a way of how you can now scoping, shadowing here. So before you move on, take a time to analyze this code using the various technique and metaphor we have covered in the book in the particular, and make sure to identify the marble bubbles colors in this snippet. It is a good practice. So here we have is the global scope, right? So this is the global scope, and then on the global scope we do have is this. We'd say, hey, scope manager. Remember, this is now the on the compilation phase. Hey, the scope manager of the global scope. Compiler here. Compiler here, yes. I got now this student name identifier. Do you have them? And the global scope say, hey, no, I don't. Let me create that. Okay. Hey, scope manager of the global scope. I do have now is an identifier and a function declarations called print student. Do you have them? No, I don't. Let me now create that for you. And then once it defined is this declaration, all right, it now goes to the next step, which is, hey, scope manager, hey, scope manager, hey, exactly, hey, scope manager, the engine here of the global scope. I need to assign is this value to an identifier called student name. Do you have any reference? Yes, I do. All right. So it's analyzing this and that. So it's analyzing the global scope as well as the function here. The global unshadowing trick. And copying is not accessing. Illegal shadowing. And function name scope here. Oh, there you got it, exactly. As you have seen by now, a function declaration looks like this, and discussed in chapter 1 and chapter 2, such functions declaration will create an identifier in the enclosing scope. In this case, the global scope, name ask question. What about these programs? So ask questions like this. The same is true for the variable ask question being created, but since it is function expression, a function definition uses a value instead. This is exactly what is a function expression? It's a function definition uses a value here instead of a standalone declarations. The function itself will not hoist, which is something we're going to see in the chapter 5. One of the major difference between functions declarations and function expression is what happens to the name identifier of the function. So consider a name function expression. Let me take a look at, okay. You have, it's okay. So one major difference between function declaration and function expression is what happens to the name identifier of the function. Consider a name function expression here. One major difference between function declaration and function expression is what happens to the name identifier of the function. Consider a name function expression like this. We know that ask questions ends up in outer scope, but what about the of the teacher identifier? For formal function declaration, the name identifiers ends up in the outer enclosing scope. So it may be reasonable to assume that's the case here. But of the teacher is declared as an identifier inside the function itself. But of the teacher is declared as an identifier inside the function itself. Exactly. So we can have now a reference to this, or we can call this function or have a reference to this. So the function of teacher here. Actually, the of teacher is not exactly in the scope of the function. Appendix A implies scopes. We'll explain further. Not only is of the teacher declares inside the functions rather than outside, but it's also defined as read only. So you cannot assign that, and it's defined as that's read only, because we use a strict mode the assignment failure as a type error. In non-strict mode, such assignment fails silently with no sections. And what about the function expression and has no name? Right? So what about a function expression that has no name? A function expression with a name identifier is referred to as name function expression. But one without a name identifier is referred to as an anonymous function expression. Anonymous function expressions clearly have no names identifier that affect either scope. We'll discuss name versus anonymous function expression in much more detail, including what factors affect the decisions to use one or the another in Appendix A. And then we look now at the arrow functions. In EXX added an additional function expression forms to the language. Call arrow function like this. The arrow function doesn't require the word functions to define it, and also the parentheses around the parameter list is optional in some simple cases. Likewise, the curly braces around the function body is optional in some cases, and when the curly braces are omitted, a return value is sent out without using a return keyword. The attractiveness of the arrow function is often sold as shortened syntax, and as they claim to equate to objectively more readable code. This claim is dubious at best, and I believe outright misguided. We'll dig into the readability of various function forms in Appendix A. Arrow functions are lexically anonymous. So they don't have any identifier bound to this, meaning they have no directly related identifiers that reference to the functions. The assignments to they are lexically anonymous. Okay, so they don't have any tokens, an identifier associated with it. They are lexically anonymous. Creates an inferent name of ask question, but that's not the same thing as being non-anonymous. The assignment to the ask questions create an infer name of the question, but that does the same thing as being anonymous, as being non-anonymous. Arrow functions achieve their syntax brevity at the expense of having to mentally juggle a bunch of variety for different form conditions. Just for a few one. This is an arrow function. This is another arrow function. This is an arrow function that returns a fixed value. This is an arrow function that takes a parameter and returns that method here that I did to uppercase. This is an arrow function that now it takes two parameters and returns now an object. Holy fuck. This is an arrow function that receives a series of arguments, and then return now is the value at that position. The value that, okay, it returns now the arguments, the last argument here. Exactly. It's returning you now is the last element value from the array, from the arguments. The real reason I bring up a arrow function is because of the common but incorrect claim that arrow functions somehow behave differently with respect to lexical scope from the standard functions. This is incorrect. Other than being anonymous and having no declarative form, arrow functions have the same lexical scope rule as functions do. An arrow function with or without here around its body still create a separate inner bucket or scope. Variable declaration inside their nested scope bucket behave the same as in the function scope. Exactly. Variable declaration inside of the nested scope bucket behave the same as this. And then back it up. Back in. Back in. Back it up. Back it up. What is back it up? Back out. To decide not to do something that you say you will. Oh, okay. Back it up. I back up. Back it up. To break a promise or agreement. Oh, it's like I regret. Back it up. When a function declarations or expressions is defined, a new scope is created. The position of the scope nested inside one another. The position of the scope nested inside one another create a natural scope hierarchy throughout the program, called the scope change. So the scope change controls variable access directionally oriented upward and outward. Each new scope offers a clean state, a space to hold it its own to set on variables. When a variable name, each new scope offers a clean state, a space to hold its own set of variables. When a variable name is repeated in different levels of the scope, shadowing occurs. And I prefer to, back it up. But why? I don't think this terminology, back it out, is to break a promise? Back it out. Really? So when a function declaration or expression is defined, a new scope is created. This structure, which is defined before the code is executed and is one altered by runtime conditions. So the position of this scope nested inside one another create a natural change of scope. It creates a natural scope hierarchy throughout the programs called the scope change. And the scope change controls variable access directionally oriented upward and outward. Each new scope offers a clean state, a space to hold its own set of variables, and where a variable name is repeated in different levels of the scope change, shadowing occurs, which prevents access to the outer variable from that point inward. Exactly, which prevents access of the outer variable from that point inwards. As we step back up from these finer details, the next chapter shift focus to the primary scope all JavaScript include. the global scope. So when we look at the appendix here, exploring further. Okay, function name scope, anonymous versus name function, and explicit or inferred names. And the missing name. And who am I? Names and descriptors. Names and descriptors. Look up the records and some data. .then function extracts sales records. Exactly. Extract sales records here. Arrow function. Arrow functions are always anonymous, even if rarely, and immediately invoke function expressions here. Hosting functions and variables. In chapter 5, but this is hosting. Okay, this is chapter 5. Article both function hosting and variable hosting. Okay, but this is not the appendix here. Anonymous function versus name functions. Okay, so we'll explore now a number of nuance and edge cases around many of the topics covered in the main text of this book. This appendix is optional, supporting material. Some people find diving too deep into a nuance corner cases, and various opinions create nothing but noise and distractions. Supposedly, developers are better served by sticking to the commonly tread paths. My approach has been criticized as being impractical and counterproductive. I understand and appreciate that perspective, even if I don't necessarily share it. I believe it is better to empower my knowledge on how things work than just gloss over detail with assumptions and lack of curiosity. Gloss over detail with assumption. Ultimately, you will encounter situations when something bubbles up from a piece that you haven't explored. In other words, you won't get to spend all your time riding on a smooth, happy path. Would you rather be prepared for the inevitable bump of off-roading? In this case, yes. This discussion will also be more heavily influenced by my opinions than my main text was. So keep in mind as you consume and consider what is present. This appendix is a bit of a collection of mini blog posts that elaborates on various book topics. It is long and deep into the weeds, so take your time and don't rush through everything here. Implied scope. So scope are sometimes created in non-obvious places. In practice, this implied scope don't often impact your program's behaviors, but it is still useful to know they are happening. Yes, keep an eye out for the following surprising scope: parameter scope and function name scope. The implied scope, parameter scope, and function name scope. Parameter scope. The conversation metaphor in chapter 2 implies that function parameters are basically the same as local declared variables in the function scope, but that's not always true. Consider as this. Here the student ID is considered implies that function parameters are basically the same as local declared variables in the function scope, but that's not always true. Here student ID is considered a simple parameter, so it does behave as a member of the Bluetooth function scope. But if we change it to be a non-single parameter, that's no longer technically the case. Parameter forms consider non-simple include parameter with default values. Rest parameters using the structure in here. So student ID. Here the parameter list essentially becomes its own scope, and the function scope is then nested inside of that scope. and the function scope is nested inside of that function, inside of that scope. Why? Why different does it matter? The non-simple parameter forms introduce various corner cases. So the parameter list becomes its own scope to more effectively deal with them. So the parameter list becomes its own scope here. Okay. Assuming left to right operations, the default max ID for the student ID parameter require a max ID to already exist and to have been initialized. This cause produce a TDC error. Chapter fee. The reason is that max ID is declared in the parameter scope, but it's not yet being initialized because of the order of the parameter. If the parameter order is flipped, no TDC occurs. So it is creating its own scope. The complication gets even more in the width if we introduce a function expression into the default parameter position, which then can create its own closure. Over its implied parameters. So in other, holy fuck. Of course, this particular nuance sometimes you might or not need to go with, but since parameters create its own scope, it also creates its own closure here. So for example, this one. Really? So for example, this one. So if you say the ID, and then you assign now a default value here with the ID, so it say, hey, I am creating is a scope of this, that the function's scope will be nested inside of this function parameter. It means that by the time I execute this, of course I'm shadowing this. So if I do this, it's gonna print 3. But if I do now it's gonna print now 3, but if I do now this, it's actually now shadowing that. It's actually shadowing this, and then it's actually shadowing. Holy hell. Okay, this snippet probably makes sense because the default ID arrow function close over the ID parameters, which when then reassigns to 5. But now let's introduce a shadowing definition. Exactly, but now let's introduce a shadowing definition of the ID in the function scope. So for example here, so now if we are introducing is the shadowing concept here, now it becomes now 3. The var ID is shadowing the ID parameter, but the closure of the default ID function is over the parameter, not the shadowing variables. The closure here is over the parameters, not the shadowing variables. Exactly, because you create, okay, function is over the parameter, not the shadowing variable in the function body. This proves that there is a scope bubble around the parameter list. But it gets even crazier than that. So if you define this local variable here, so if you define this console local variable ID, and then you say, hey, this will be now the ID, all right, $ID. So you might assume that, well, actually it tries to access to the ID, right? It means that it's lexical. And then you say now parameter ID closure, exactly, which is the parameter ID closure, because it's creating is close. Okay, you create a closeover at the parameter scope. Okay, and then when you reassign ID to 5, okay, what this ID will happen? Well, I'm assuming that it's going to resolve this into this var, right? Reassigning ID to 5. So the local variable ID must be 5, and the parameter ID closure must be whatever it has previously, right? Which is the local parameter ID, and the local parameter, exactly, reassigning ID, local variable ID is 5, and the parameter ID closure is 3, exactly. And the local variable ID here is 3, so it's making a reference to not the ID. Okay. The strange bit here is the first console message at the moment the shadowing ID local variable has just been var ID declared. With chapter 5, assert it is typically auto-initialized to undefined at the top of its scope. Why doesn't print undefined exactly? In this specific corner case, for legacy compact research, JavaScript doesn't auto-realize ID to undefined, but rather to the value of the ID parameter 3. Though the two ID looks at the moment like they are one a variable, they're actually still separate and in the separate scope. The two ID looks at the moment like they are one variable and they're actually still separate and in separate scope. And the assignment makes the divergence observable, where the ID parameters stay 3 and the local variables becomes 5. My advice to avoid getting bitten by these nuance weirs: never shadow parameters with local variables. Never shadow parameters with local variables. Avoid using never shadow parameters with local variables. Avoid using a default parameter function that close over any of the parameters. At least you're aware and can be careful about the fact that the parameter lists in its own scope if any of the parameters are non-simple. And the other is so what happened here is that it's creating that. Never shadow parameters with local variables like this. Shadowing. So so when you define a variable with the same name, exactly, when you define a variable with the same name in deep scope, you are creating is now a shadowing. So in other words, never shadowing local variables. Never shadow parameters with local variables. And function name scope. In the function name scope section section in chapter 3, I assert that the name of the function expression is added to the function own scope. That the name of the function expression is added to the function's own scope. So it is true that of teacher is not added to the enclosing scope, where ask question is declared, but it's also not just added to the scope of the function, the way you're likely assuming. It is true that of teacher is not added to the enclosing scope, where ask question is declared, but it's also not just added to the scope of the function. They are the way you are likely assume. In another strange corner case of implied scope, the name identifier of a function expression is its own implied scope. Why is this not duplicate declaration error? Confused yet? So if the of teacher was in the function scope, we expect an error here. Let declaration form does not allow redeclarations. Exactly. But this is perfectly legal shadowing. So any time you declare an identifier, anytime you have two identifiers as a variable or as a function with the same name nested each other, you are creating is a shadowing. But this is perfectly legal shadowing, not the redeclaration, because the two of the teacher identifiers are in a separate scope. You rarely run in any case where the scope of a function's name identifier matters. But again, it is good to know how this mechanism actually works to avoid being beaten and never shadow functions names identifiers. Okay. And then we have now chapter 3 here, explicit or inferred names. As discussed in chapter 3, functions can be expressed either in name or anonymous form. It is vastly more common to use the anonymous form, but is that a good idea? As you contemplate naming your function, consider name. Inference is incomplete. Lexical names allow self-reference. Names are useful descriptions, and an arrow function has no lexical names. Immediately function expressions also need names. Explicit or infer. Set timeout, wait a moment, and all uppercase. Okay, yeah, this is more opinionated. Especially if you're gonna pass a function instead of an arrow function, pass now a function description that indicate that, hey, what in the French toast are you doing. Our name, right? You say not name. You say that name is not name, and the config.cb.name is cb. These are reference to us infer name, and the other is missing names. And who am I? And named are descriptors. Lastly, I think most important of all, leaving off names from a function make it hard for the reader to tell what function purpose is at quick glance here. Keep only odds. There are just not reasonable argument to make that omitting the name keeps only here and keeps only here. Exactly. When you are mapping here, names are descriptors of the functions, and similar for the arrow functions. If you have used to hack like this, or you prefer to call .bind this or inner function expression, you force them to inherit a this. from an other function like it was lexically available, then arrow functions are absolutely the better option. They are designed specifically to fix that problem. So in the rare case you need lexical this, use an arrow function. It is the best tool for that job. But just be aware that in doing so, you are accepting the downside of anonymous function. You should expend additional efforts to mitigate the readability costs, such as more descriptive variables named and code comment. Mm-hmm. Mm-hmm. And more common. Okay, so that'll be all for this video. Take care. Bye bye.